Hey guys, and welcome back to another episode of Physics in 5, and today, as promised, we are covering the wave-particle duality of light. Why isn't that on the board? What an idiot. Okay, yeah, so of light. And as this video is in reference to the electromagnetic spectrum video that I put up as my first ever Physics in 5 video. And so I'll leave a link to that video there, give myself a cue. So if you haven't checked that out already, check that out. And if you haven't checked out the superposition video yet, go and give that a look. I'll leave a link to that here, because that really explains why light can behave as a wave. So that's quite important as well. So actually I'll probably leave the link to that there on Wave. So yeah, let's go. Words, man, words. So what do we mean when we say wave-particle duality? What does that actually entail? So what we're saying is that light can travel as both a wave and as a particle. And if you've seen that electromagnetic video, then you'll know that light is an electromagnetic wave, which is energy released when an electron loses energy. And we call that a photon. But light is a wave, but light is a particle. How does that happen? How do we know that that happens? That's what this video is going to be about. So the first part of this duality is the wave duality, and in 1807 Thomas Young performed his double slit experiment. Now this is an absolutely terrible drawing, so what I'm going to do is put the pictures up and talk over the pictures about the experiment quickly. But for this to happen, we have to understand what diffraction is, because diffraction is what causes this single beam of light to spread across the whole thing, right? So diffraction is the bending of light, and if the slit or the gap that the light has to pass through is comparable in size to the wavelength of the light, then this sort of bending of the light will happen. And the same thing happens when the refractive index of something is changed. So for example, light passing through a swimming pool or the sea, or through a raindrop that gives that allows us to see the colours of light spread out into a rainbow, for example. So just wanted to get that down, that this can only happen when we consider light as a wave. Let me tell you the story of Thomas Young and his double slit experiment. What we have on screen is a very basic version of his experiment, and it's often called the Young's slit experiment, or just Young's experiment. And what it requires is a coherent light source, which we usually use a laser for. Then we can guarantee that the light is always the same wavelength. The light passes through the first slit so that it diffracts, so that it spreads, so that we can get it to go through two slits at the same time. Once it goes through the two slits at the same time, it then diffracts again into two patterns. And then at that point we get the interference, so we get the superposition, so we get bright spots and dark spots, which are marked as BD, BD, B. Although that wouldn't happen if light didn't behave as a wave, because to get those bright spots and those dark spots, we have to have wave interference. So this experiment took place way before quantum mechanics was even considered, and over the years it's developed so that we find that detectors pick up these individual particles, these individual spots of energy, rather than just bright patches. Now if we fast forward another 100 years to Albert Einstein's photoelectric effect, this cannot be explained using the classical theory that light is a wave. He noticed that shining blue light onto a metal released some electrons, and this cannot happen if light behaves as a wave. So the photoelectric effect is actually quite an interesting one. It's more of a collaboration of scientists rather than just Albert Einstein. In 1887, Heinrich Hertz discovered that when he illuminated electrodes with ultraviolet light, that it was easier for him to generate a spark. And then Max Planck and Albert Einstein both discovered that for this to happen, light must be some form of packeted energy, and it was later discovered that this was known as the photon. And what's actually happening here is that the photon arrives as a packet of energy within the light beam, let's call it, and that energy is then transferred to an electron within the conductor to give that electron enough energy to break its bond with the atom. And the equation is up on screen now. And so there must be some energy that we call the work function that keeps these electrons in the conductor, and that energy is then lost. That is the energy that the photon must give to get the electron to escape. But of course we already know that everything wants to be in its lowest possible energy state, so these electrons will then go on to emit other photons. Okay guys, so thanks again for watching this video on wave-particle duality of light. I hope it really helped. Like I said at the start of the video, this is linked to the electromagnetic wave physics in 5 video I've already done, so I'll leave a link maybe here? Yeah. If you haven't already, hit that like button, it really helps. Subscribe to the channel if you want some more, and check me out on social media at JMJournalism on both Facebook and Twitter. So yeah, I'll see you next time guys, thanks for watching.